Welcome to our very first lecture video. So in this first chapter, it's called Chapter P. Everything in here is supposed to be prerequisite knowledge. Now, just because it's supposed to be prerequisite knowledge doesn't always mean that that's the case. Some of you, it may have been a while since you've been in a math class, so this will hopefully be a good refresher for you to have the skills needed in order to do well in the rest of this class and in future classes. So the way that I will do all these videos is I'll prepare the notes and then I'll go through them with you here online. But now, as far as working the more rigorous, fun homework problems and stuff, like what you'll see assigned on my math lab, all you ever have to do is look at my homework assignments. So in addition to these videos, every single problem that you've been asked to do on my math lab, I've worked a similar problem out of the homework. The way I generate my math lab questions is straight out of the homework questions. It gives me the opportunity to regenerate a problem on my math lab. So you can refer to my homework at any time to see a problem just like what you're being asked to do on my math lab. And throughout the course, if you need some help with those, I'd love to help you out with that as well. So you can just let me know at any time, and I'll be glad to look at those with you. But now, without further ado, let's go ahead and get into our first section here. So first section, like I said, we're in Chapter P, and this first section is the very, very, very early prerequisites. But there's a bunch of them. This is kind of a packed section P1. So going ahead and looking at this with you here, P1 objectives. We're going to evaluate algebraic expressions. So that just means plugging in numbers for variables within an expression. It could also mean plugging in different variables for variables in an expression. So like if you have an expression in terms of f of x, what if I ask you to evaluate it at f of r plus s or something like that. Now the second thing here is I say use mathematical models. Anytime you see the word mathematical models, you should be thinking, ooh, a nice application word problem. So we need to be able to change English words into mathematical words and then be able to figure things out from that. Now some things you may or may not be too familiar with. We're going to find the intersection of two sets and the union of two sets. We'll talk about that later. Recognize subsets of real numbers. Use inequality symbols. Evaluate absolute value. That's absolutely important. And then the most common use of absolute value is it's used to represent distance, since it's really improper to say, hey, the distance from here to the store is -3 miles. That just doesn't make sense. You'd say it's 3 miles because the distance from here to the store is 3 miles, and regardless of direction. Identify properties of real numbers and then simplify algebraic expressions. Okay, so that's a lot. Let's go ahead and get into it. The first step here, algebraic expressions. With algebraic expressions, we just know that it has to be in terms of various letters and numbers that we'll be calling a variable because we don't know what they are. A combination of variables of numbers using operations of addition, subtraction, multiplication, or division, as well as powers, roots. All of this can be in an algebraic expression. Now notice, it doesn't have to be an equation. An equation has an equal sign. If it doesn't have an equal sign, we can still call it an algebraic expression. Now when we evaluate an algebraic expression, it means to find the value of the expression for the given value of the variable. So we plug things in for those letters that are called variables that we don't know in the given problem. B to the n is called an exponential expression. We can still call it an algebraic expression, but anytime you have a variable exponent and a constant base, the variable is in the exponent, thus we call that an exponential expression. Now, first thing, we're going to go ahead and look at evaluating a simple algebraic expression. In this case, if I ask you to evaluate 8 plus 6 times the group x minus 3 quantity squared, and I'm wanting you to evaluate that for x equals 13, you say, hey, no problem. all you're going to do is take that expression and you're going to plug a 13 into the place that x was. So please notice from this step to this step, all I did is I replaced x with a 13. And now you have to use your order of operations. Order of operations, I always just remember the word PEMDAS, parentheses, exponents, multiplication and addition in order from left to right, and then addition and subtraction in order from left to right. So in this case, I say 13 minus 3 is 10. Then we'll have to square that 10 to get to a 100. Then we know multiplication comes before addition, so we'll have 600 plus 8. Our final answer after we evaluate is 608. Pretty cool. Okay, up next, formulas and mathematical models. It says an equation is formed. This is what I was talking about back on the first page. A lot of times when I ask students what's the difference in an expression and an equation, and they just kind of look at me and say, I don't know. An equation has an equal sign. So an equation is formed when an equal sign is placed between two algebraic expressions. A formula is an equation that uses variables to express a relationship between two or more quantities. The process of finding formulas to describe real-world phenomena is called mathematical modeling. In other words, just application problems. Now let's go ahead and look at one. In this problem, you're given the formula t, where t is equal to 4x squared plus 330x plus 3,310. And you're told that that models the average cost of tuition and fees t is the total cost of tuition and fees, for U.S. public colleges after the school year, during the school year ending X years after the year 2000. Okay. So we're supposed to use the formula to project the average cost of tuition and fees in U.S. colleges for the school year ending 2014. Now, we're to assume that this is still true up to this day here in 2020, but it's asking us to go ahead and evaluate it in 2014, and it doesn't give us when this formula is no longer valid. So it could be valid, to 2030, 2050. The longer X is, the less I would believe the formula to be accurate. But for this example, we're just saying, well, X is just 14. It should be accurate up to that amount. So X equals the number of years after 2000. So in this case, 14 years, 2014 minus 2000, you get a 14-year differential. So you substitute 14 in for X, and it's going to be pretty straightforward. So here's my equation. I took that equation. All I'm doing is I'm substituting a 14 in for X. So you should be thinking, well, this is pretty straightforward, pretty easy. Yeah, absolutely. Now, order of operations here. You square the first 14, 14 squared, 196. I'll just leave everything else because technically I should go ahead and take care of the exponent before doing anything else. Now, once you've done that, you can say, well, the only thing left is multiplication and addition. Multiplication comes before addition. I multiply 4 times 196, I get 784. Multiply 330 times 14, I get 4,620. Now I add all three numbers there, and I can see that this is giving me that in the year 2014, the average cost at a public college for tuition and fees came to $8,714. Okay, up next, I want to talk about sets and set notation. I always struggle drawing these out by hand. And what I mean is the brace that you see here. It says a set is a collection of objects whose contents can be clearly determined. The objects in the set are called the elements of the set. We use braces to indicate that we are representing a set. So for example here, I'm saying brace, and then everything in there is the set of what I'm referring to. Well, if I'm saying 1, 2, 3, 4, 5, and then anytime you see the dot, 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 it means it's going to continue on in that pattern. So I'm supposed to assume, oh, this is just like the counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, keeps on going on and on and on forever. So this is an example of the roster method of representing a set. The 3 dots after the 5, it's called an ellipsis, indicate that there is no final element and that the listing keeps on going on forever and ever. So anytime you see that, you have to understand that just means that the set keeps on going. Go back here. Oops, no. There we go, guys. Sorry. Now, it says if a set has no elements, and this is something I do want you to know, it's called the empty set. So especially later on, whenever we start asking the intersection of two sets, well, if two sets don't have anything in common, then your answer is going to be the empty set. And the notation for the empty set, it looks like a 0 with a slash through it. So please don't just put a 0, because that would mean 0 is in common. 0 with a slash through it means there are no elements in common between the two sets, or in other words, the empty set. Okay, now, up next. Set builder notation. This is a notation I'm not that crazy about, but your book uses it, so we need to go ahead and talk about it and be familiar with it. It's called the set builder notation. My favorite notation is just interval notation, and we'll also be talking about that. But the set builder notation, you'll always open it up and say, well, it's the set of all x such that x, and this is how it's read right down here, the set, that brace there means the set of all x such that, that vertical line means such that, x is a counting number less than 6. Okay, well, how would I represent the set of all numbers, counting numbers less than 6? The counting numbers are the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, the ones that are less than 6 are the numbers just up to 5. So unlike the one on my previous page where I kept on going beyond 5, this time if it's the counting numbers less than 6, then I stop abruptly at 5 and I close out my set. Now, keep in mind, whether your set has a terminal number, like in this case, 1, 2, 3, 4, 5, or in the other case where it does not, you still have to end with that brace to designate the set notation. Now, definition of intersection of sets. If I want to say the intersection of sets A and B, it looks like A in B. It's A intersect B. It's just like a really high uppercase N. A intersect B is the set of elements common to both set A and set B. So it's only in the intersection if it's in both sets. The definition can be expressed in set builder notation as A intersect B is X such that X is an element of A and X is an element of B. Okay, so you might be thinking, well, I'm not exactly sure what that means. This should make it clear to you. So notice here, I have you define the intersection between the set of numbers 3, 4, 5, 6, and 7, and then the numbers 3, 7, 8, and 9. So if I want the intersection of these two sets, any element that's in the intersection must be in both the first set and the second set. So you say, well, okay, why about 3? Yeah, it's in both sets. So the first set intersected with the second set would contain 3 because it's in both sets. Would it contain 4? Nope, not in the second set. Would it contain 5? Certainly not. 6? Nope. 7? Absolutely. So only 3 and 7 are in both the first and second set. Now, that's exactly the way I would think about intersections, is I would just look at that first set and say, is that number also in the second set? And if it is, then it's in the intersection. If it's not, then it's not in the intersection. And then you're done after you finish that first set, because if there's a number in the second set that's not in the first set, clearly it's not in the intersection anyway. Now, the union of sets. And actually, unions are used a little bit more commonly than intersections. The unions of set A and B, it's written as A union B. It looks like a U there. And if you put a U, I'm not going to get mad on a test or anything. It's fine. A union B. It's the set of elements that are members of both set A or set B. Now, this definition can be expressed in set builder notation as A union B consists of the set of all X such that X is an element of A or X is an element of B. All right. Now, We can find the union of sets A and set B by listing the elements of set A, and then you include the elements of set B that have not already been listed. So this is, again, it's a pretty straightforward process. Let me show you what I mean. So I go back to that same problem with this set 3, 4, 5, 6, and 7, and then the set 3, 7, 8, and 9. So automatically, if I'm trying to state their union, I would go ahead and just put the entirety of the first set. So we know it's 3, 4, 5, 6, and 7 because that's at least in the first set. And then you go to the second set and say, okay, what elements does this set contribute that the first did not already have? Well, 3, it's already in there. 7, it's already in there. The 8 and the 9, oh, that's not in there. I have to include it in the union because the union says it can be in the first set or the second set. So the set of numbers 3 through 7, union with the set of numbers 3, 7, 8, and 9 gives me the set of numbers 3 all the way up to 9. And again, remember, for this set notation, you have to start with a brace and end with a brace. Now, the sets of the real numbers. I referred to these as counting numbers earlier, and they are referred to as counting numbers. I said counting numbers less than 6, or we was referring to the numbers 1, 2, 3, 4, 5, and 6. Well, another word for counting numbers is the natural numbers. Natural numbers are going to be whole numbers starting at 1. So you go 1, 2, 3, 4, 5, 6, 7. Same thing as the counting numbers. Now, all of these are subsets of real numbers. The number system is broken up into real numbers and imaginary numbers. We will definitely be dealing with imaginary numbers later on, where you have the square root of a negative number. But for now, mostly we'll be dealing with the real number system. Now, the natural numbers are counting numbers starting at 1. Whole numbers doesn't contribute much more to that. It just includes the 0. Sometimes you need to keep that in mind, the difference between those two. It's just whole numbers includes the 0, natural numbers does not. Now, integers, again, it's whole numbers, but it's going to also contribute all of the negative values in there. So instead of just 0 through infinity in the integers, we have all of those values plus the negatives of those values. Now, the set of rational numbers is any time a number can be rewritten as a fraction. And a fraction means that in decimal format, it would either have a repeating decimal or an ending decimal. So if that's the case in decimal format, it can be written in some format of A over B. And of course, as long as B does not equal 0, because then the fraction would be undefined. That's the set of rational numbers. Now, you almost might think, well, isn't that all the different types of real numbers? No, there's plenty of numbers that are not rational numbers, and those are the irrational numbers. They're still real numbers. We just can't ever quantify them exactly. That would be like pi, that's 3.1415927, or the square root of 2, which is 1.41442, square root of 3, 1.7321426. It keeps on going on and on and on. We can't ever quantify it exactly. Those are irrational numbers. You can't ever have an ending decimal or rewrite it as a fraction. Now, you'll see here on this next page where I try to give you a visual representation. Real numbers can be broken up into rational or irrational. And then within the rational numbers, notice irrational numbers, it doesn't have any subdivisions. It's its own thing. But then rational numbers, you can break it up into integers, which are positive, negative, whole numbers. And then whole numbers, which start at 0, and then natural numbers, which start at 1. Okay, so now if I ask you to consider the following set of numbers, -9, -1.3, 0, 0.3 repeating, pi over 2, square root of 9, and the square root of 10. Okay, so I'm asking you to list the numbers in the set that are natural numbers. You say, well, it has to be whole numbers that start at 1. So clearly the first two cannot be natural numbers because they're negative. The third one cannot be because it's 0. Next one cannot be because it's not a whole number. Pi over 2 isn't because pi over 2 is like 1.57. The square root of 9, ooh, square root of 9 is 3. Ding, 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 ding. So you can say, the only natural number within this set of numbers in the square root of 10, it's going to be an irrational, it's a never-ending decimal. So the only number in this set that is a natural number is just the square root of 9, and it's because the square root of 9 is 3 there. Now, if I ask you to list the whole numbers, you'd say, well, of course, I would have to still include the 3 because that's a natural number, and whole numbers include natural numbers, but whole numbers also include a 0. So you'd say the whole numbers in this set are 0 and 3. Now, if I said list the numbers in this set that are integers, you'd say, okay, integers will just include whole numbers that could be positive or negative or 0. So we'd still have our 0, we'd still have our 3. None of these are going to be integer values. That's not an integer value. Negative 9 is, though. So you'd say, well, I know that the numbers in the set that are integers are going to be the positive, negative, whole numbers, and 0, negative 9, 0, and 3. Now, if I say list the rational numbers, you say, okay, every single integer value is also a rational number, and it would also include any number that can be rewritten as a fraction or an ending decimal or a repeating decimal term. Okay, so almost all of these are rational. You'd say, is the first one rational? Yeah, because it's a whole number. Is the second one rational? Yes, because it has an ending decimal. The third one's an integer, thus it's a rational. The fourth one, that is a repeating decimal. 0.3 repeating could be rewritten as 1/3, therefore it's rational. Pi over 2, anytime you see anything with pi that's a never-ending number, does it matter that it's divided by 2? No, still a never-ending number. Square root of 9 is 3, therefore that's rational. Square root of 10, not a rational number. If you go to your calculator, you'd see that it's a, in this case, I'll go to mine real quick, square root of 10, it's 3.16227766. Now, it actually sounds like it has a pattern. I promise you it doesn't. It would go on and on and on forever. Now, list the numbers in this set that are irrational numbers, and that's what I was just talking about with the square root of 10, and also the pi over 2. They can never, ever be rewritten as a fraction, thus they would be irrational. Now, inequality symbols. If we talk about inequality symbols here, the first one, if I say A less than B, with that sign, you've probably had teachers always tell you small side goes to the small number, large, or some teachers would say large mouth, large number, small mouth, small number. You could just say large side, large number, small side, small number. This is A is less than B. A is less than B. Now, if you see this sign, it means A is less than or equal to B. This would mean A is greater than B, and then A is greater than or equal to B. When comparing the size of real numbers, we are ordering the real numbers from low to high. Now, the absolute value of a real number is denoted as the absolute value of A. Now, this is something I see students, even in calculus classes, forget. Whenever you have an absolute value, that they forget that it could be rewritten as a piecewise value of that same number. If I'm talking about the absolute value of A, that absolute value does absolutely nothing if the number on the inside is already positive. So the absolute value of A is just A if A was already greater than or equal to 0. Now, of course, that should make sense to you. But now keep in mind that absolute value of A, it's going to be equal to the negative of A if A was less than 0, because it's going to have to change the sign of that negative number. So if you had the absolute value of negative 8, you just say, well, it's 8. Well, you're taking the negative of negative 8 in order to do that. Now, next page here. Case in point. If I ask you to rewrite the expression without the absolute value bars, I think a lot of students would struggle with this one. They'd say, okay, do I just change both of their signs? Well, think about it. In this case, yes, you would. Why would you? Well, because on the inside, 1 minus the square root of 2. The square root of 2 is like 1.414. We're going to have 1 minus 1.414. The inside would be a negative 0.414. You know the absolute value is going to change the sign of that. It has to make it a positive 0.414. So if you're changing the sign of the answer once you simplify, then you can just change the sign of both terms within and say, well, okay, then it would be -1 plus the root of 2, which that would be fine. Or you could just say the root of 2 minus 1. It looks a little better. So the absolute value of 1 minus the root of 2 is the root of 2 minus 1, because that absolute value is going to change the sign of that expression. Now, what about the expression, the absolute value of pi minus 3? You say, okay, pi is 3.1415926. When I subtract 3 from that, it's going to stay positive. So that absolute value does absolutely nothing in that case. So we can just say, well, then the absolute value of pi minus 3 is simply pi minus 3. Now, when we're talking about the distance between 2 points, if I say if A and B are 2 points on a real number line, then the distance between A and B, I can either say, well, it could be A minus B, but now, what if you say A minus B and A is a smaller number than B? Then you might think, well, the distance is negative. Well, then you just say, okay, in order to make it positive, I can stick an absolute value around it. So it really doesn't matter whether you subtract the smaller number from the larger number or the larger number from the smaller number. That's what I'm trying to say here, is that the absolute value of A minus B is going to be the exact same thing as the absolute value of B minus A. You could try putting some numbers in there. 2 minus 5 would be -3. Well, the absolute value of -3 is 3. Well, that's the same thing as the absolute value of 5 minus 2. It'd be the absolute value of 3, also 3. So you can just say, inside of an absolute value, the order of that subtraction sign, completely irrelevant. Now, if I wanted to find the absolute value of the distance between -4 and 5, you'd say, well, all right, does it matter which one I start with? Actually, it doesn't. Now, myself, just to avoid changing the sign, I always do right minus left. So I would say 5 minus a -4 and get a 9 on the inside. But I purposely did it the other direction down here and said, well, what if I start with the left and then subtract the right? -4 minus 5, you get a -9 on the inside, but the distance between them is not -9. It doesn't make sense to say the distance is negative. So the absolute value we just say is 9. And we say, oh, okay, the distance between those 2 points on the number line they're 9 units apart. Now, properties of real numbers, the biggie here is the distributive property. I want you to be extremely comfortable with that. Now, here I have a monomial times a binomial, but it doesn't matter how many terms are in each one. Anytime you're multiplying expressions, every term of one expression must multiply every single term of the other expression. In this case, A times B plus C is AB plus AC. Now, the identity property, you know, if you're wanting to not change a term and you're adding something, well, then the identity property of addition is you can add a number 0 to any number, doesn't change that number. Doesn't matter the order at which 0 is added. That's why 0 is the identity property for addition. Similarly, for multiplication, the identity is you can multiply any number by 1, and it doesn't matter if you multiply it as the second term or the first term, remains unchanged. Now, simplifying algebraic expressions. To simplify an algebraic expression, you simply combine like terms. Now, what do we mean when we say like terms? Notice, like terms are terms that have exactly the same variable factors. An algebraic expression is simplified when the parentheses have been removed and like terms have been combined. Now, let's make sure you see what we mean in that case. So here I'm trying to cover the distributive property and the simplification property within one problem by asking you to simplify this expression. 7 times the group 4x squared plus 3x plus 2 times the group 5x squared plus x. So the first thing I'm doing here, and you do not have to show this many steps, this is just really trying to break it down for you, is I would need to distribute the 7 into both of the terms in that first group, and I would need to distribute the 2 into both of those terms in the second group. Okay, of course, when you do that, you're going to get 7 times 4x squared for 28x squared. Then you'd have plus 21x. 2 times 5x squared gives me plus 10x squared. then I'd have 2x. Now, when you're combining like terms, well, you can notice the first and third term are both x squared terms. Like terms are same variable factors to the same power. So I can combine those two and say, well, my next term is just, I'm going to say 28x squared plus 10x squared. You add the coefficients to get 38x squared. I did the same thing with the like terms of x to the first. 21x plus 2x is 23x. Now, this is showing an abundance of steps here. You would not have to show out all of that at work. You only need to show out as much work as you need in order to know how to work the problem. This is just trying to make sure you see every step of the process. Okay, guys. Now, that was it for this first section. Please do keep in mind, as you try the problems, there is no problem assigned that I haven't first worked myself. So all you have to do anytime you run into any problems is look at what I've done on, let me make that a little bigger there, yeah, is to look at what I've done on my homework solutions, and it should correspond with everything that you're doing within the My Math Lab assignments. Now, if for some reason it doesn't, that's what I'm here for. I'll be glad to help you out whenever needed throughout the semester, so you just let me know. I look forward to working with you throughout the semester. Take care.